Have you ever wondered how engineers know exactly what's going to come out of a giant chemical reactor? Or how scientists can track every last nutrient moving through the human body? Well, it sounds super complicated, but it all boils down to one really powerful idea, just accounting for stuff. So forget the intimidating jargon for a minute. Today we're going to pull back the curtain on material balances, what is basically the universe's own accounting system.
All right, here's the game plan. We're going to start with the one golden rule that makes this whole thing work. Then, we'll get the lingo down so we can define what we're looking at and how it acts. After that, I'm going to show you the one single equation to rule them all. We'll even test it on some real-world stuff, from your car tires to your own heart. And finally, I'll let you in on a little secret, a pro tool to figure out if a problem's even solvable before you waste your time. Let's do this.
Okay, so everything, and I mean everything, we're about to talk about is built on a single, unbreakable law of the universe. This is the foundation, the absolute truth that makes all of this accounting possible. Way back in 1789, a guy named Antoine Lavoisier nailed it. What he figured out is pretty simple. You can't just create stuff out of thin air, and you can't make it vanish into nothing. Sure, it can change form, water can become steam, wood can become ash, but the total amount of stuff you started with is always what you end up with. That's our guarantee. It means the books always have to balance, no exceptions. So if we're going to be accountants for matter, we've got to learn the language, right? Before we can start balancing the books on anything, we need to be crystal clear about what exactly we're counting. First things first, the system. Now this just means whatever part of the universe we decide to focus on. And the key word here is arbitrary. You get to decide. It could be a whole factory, or it could be a tiny little cell in your fingertip. It's whatever you decide to draw a mental box around. And that imaginary box you just drew, that's called the boundary. It's the line in the sand. It separates our system from everything else out there, which we just call the surroundings. This line is so important because it's what lets us say what's in our problem and what's out. And once you have that boundary, you can sort systems into two basic types. Think about a sealed bottle of water. That's a closed system. Nothing gets in, nothing gets out. But what about a running kitchen sink? Well, water is constantly crossing the boundary of the basin, right? So that's an open system. Simple as that. Okay, so we've defined our box. We know what's in and what's out. But things don't usually just sit there. They do stuff. So how do we describe the action? How does our system behave over time? Well, there are two main flavors here. First, you have a batch process. This is just like baking a cake. You throw all your ingredients in the bowl at the very beginning, mix them up, bake it, and then you take the finished cake out at the end. Nothing's coming or going while it's in the oven. The other type is a continuous process. Think of an assembly line. Raw materials are constantly flowing in one end, and finished cars are constantly rolling out the other. It never stops.
And one last piece of the puzzle. We need to know the state of the system. Is it on cruise control or is it changing? If all the important stuff, like temperature, pressure, you name it, is holding perfectly constant, we call that steady state. But if anything is changing over time, like the pressure inside a tire while you're filling it up, then it's in an unsteady state, or what some people call a transient state.
All right, we've learned the language, we've defined the behaviors, now it's time to put it all together. You see, all of these ideas, they all feed into one single, beautiful, and unbelievably powerful equation. This is it. This is the master key that unlocks every single material balance problem you could ever imagine. But before I show it to you, just remember this. Don't let the terms fool you. Don't get intimidated. At the end of the day, all we're doing here is accounting for stuff. That's it. And here it is. Accumulation equals input minus output plus generation minus consumption. Take a second to look at that. This one little line, it governs the flow of matter everywhere, from galaxies forming in deep space to the chemical reactions happening in your own body right now. This is the heart of it all. Let's make this super simple. Think about your bank account. Input, that's your paycheck, a deposit. Output, that's you paying your rent, a withdrawal. Generation is like interest earned, money that just kind of appears in your account from a process. Consumption? That's like those annoying bank fees, money that gets used up and disappears. And accumulation? Well, that's just the change in your final balance at the end of the month. See? It really is just account. Okay, theory's one thing, but let's get our hands dirty. Let's see this master key in action. We're going to take this framework and apply it to a few real-world things that you probably see every single day. So check this out. Filling a tire. Air is going in, right? So it's an open system.
and the pressure inside is changing, so it's in an unsteady state. What about water flowing through a pipe at a constant rate? Well, that's open, continuous, and it's steady state. A cold bottle of juice sitting on your table and slowly warming up. That's a closed system. It's a batch process, and since its temperature is changing, it's unsteady state. See, you can classify pretty much anything.
Now for something a bit more intense. What you're looking at is the amount of blood by mass that your heart's left ventricle pumps out every single minute. Yeah, that's almost 5 kilograms every minute. So how on earth can we know that number so precisely? Well, you guessed it. We use our equation.
So how do we solve this? Well, first we just calculate the output using the numbers we have. But here's where the real magic happens. It's in the assumptions. We can assume that for our purposes, there are no chemical reactions happening, so generation and consumption are both zero. We can also assume your heart isn't, swelling up with blood, so accumulation is zero too. And all of a sudden, our big, intimidating master equation gets super simple. It just becomes input equals output. That's it. So the blood flowing in has to be the same 4,900 grams per minute that's flowing out. It's that elegant.
All right, time for a pro tip. Wouldn't it be awesome to know if you can even solve a problem before you spend hours wrestling with the math? Well, it turns out engineers have a slick little tool for doing exactly that. I mean, we've all been there, right? You're halfway through a really tough problem and you suddenly realize you're missing a key piece of information. It's so frustrating. There's got to be a better way to check first.
And there is. It's called a degree of freedom analysis. And honestly, it's less about math and more about strategy. All you do is count your unknowns, the things you need to find. Then you count your independent equations, the relationships you have. If those two numbers match, your degrees of freedom are zero. That's a green light. The problem is solvable. If you have more unknowns than equations, you know you need to go find more information. It's like a pre-flight check that saves you from diving into a problem you just can't solve yet.
So there you have it. We started with a simple law of the universe and ended up with a toolkit that can analyze pretty much anything, from a car engine to a human heart. You've now got a brand new lens to see the world through, a way to see the hidden accounting that's happening all around you all the time. So the only question left is, now that you have the master key, what are you going to analyze first?